Okay, hi, I'm Neev. I'm a graduate student at the University of Arizona, where I work with Matthew on all the cool things that you can form with massive binaries, which is what I'll talk about today. So thanks to Aditya's overview talk, we already got a nice overview about everything interesting we're learning about the underlying gravitational wave population and its implications for various formation channels. But to take a step back, what does one do when you detect a source that does not fit in well with the rest of your population? Specifically, I'm talking about GW 190814, which was the merger of a 23 solar mass black hole with a 2.6 solar mass compact object. And this event has been challenging to model from a population perspective, and various results such as the maximum mass of the neutron star or the presence of a supposed mass cap depend on how you treat this event and whether you include or exclude it from your analysis. Additionally, I'm also interested in the mass ratio of this event. With a Q of 0.1, it's the most asymmetric source we've seen till date. And the natural question that arises is, how do you form events like 190814? Now, in the context of isolated binary evolution, many things have to go right to form a gravitational wave source, and it can be difficult to trace back their progenitors just from gravitational waves. But thankfully, many of these intermediate stages can be observed and well studied in our own galaxy. And one of the key phases, in fact, is the high mass X-ray binary phase after the formation of the first compact object. And given the high asymmetry that we see in 190814, a natural place to look at is highly asymmetric X-ray binaries. Turns out we have at least one such system in our own galaxy, which is this high mass X-ray binary, where you have a 2 solar mass compact object that's accreting from the wind of a 45 solar mass O-type star in a tight 3.4-day orbit. And with the help of Gaia, we also know that this system is a runaway high mass X-ray binary, and it can be confidently traced back to this young cluster, NGC 6231, that is just a few million years old. Now, we think that runaway high mass X-ray binaries form when one of the stars in the binary explodes, and this explosion can give the binary a systemic velocity, which can even eject it out of the cluster. And this is actually pretty useful because then we can use the observed X-ray binary to retrace what it looked like just before the supernova. We can do this with Monte Carlo simulations where you simulate the outcomes of millions of supernovae in binaries and then select for systems that match your observed X-ray binary parameters today. When we do this with our high mass X-ray binary, what we find is that the systemic velocity can strongly constrain the mass of the progenitor of the compact object. But if we also use the fact that the binary has a very tight orbital period today, we can get a really strong constraint on both the period and the mass of the progenitor just before the supernova. And this is actually pretty useful if you want to chart the past evolutionary history of the system, which is now what I will show using MESA. So we start with two stars, 40 and 28 solar masses in a tight 3-day orbit. And because of the short orbital period, mass transfer starts on the main sequence and the donor starts transferring mass to the companion, whose evolution I've shown on the HR diagram on the right, with the blue phase showing its mass transfer phase. And by the end of the donor's helium burning phase, when it's just a few thousand years away from core collapse, it has a mass of roughly about 12 solar masses, and the companion has grown to about 43 solar masses because mass transfer remained mostly conservative. And the orbital period is about 6 days, and all three of these roughly match the observational constraints that we got from the high mass X-ray binary with our Monte Carlo simulations. And even the position of the star on the HR diagram matches with what we see today. Now, when the star explodes, it leaves behind a compact object that's about 2 solar masses, and the system might resemble the runaway high mass X-ray binary that we see today. But the question is, what is the future of this system? And when the companion star fills its Roche lobe, because of the high asymmetry of the system, it's likely going to form a common envelope, and we want to figure out what's the fate of this common envelope phase. So we can do this using the alpha lambda prescription, where I'm showing over here how the donor's radius evolves over time in orange, and correspondingly, depending on when it fills its Roche lobe, I've shown the binding energy of its envelope. Now we can convert this equivalently into the fraction of the orbital energy that would be required to eject this envelope. And given that the star is going to fill its Roche lobe at roughly around 30 solar radii, we find that the alphas needed are much more than 10, which means that this common envelope phase is likely going to fail, and we might form a premature merger or even a Thorne-Zitka object. So we showed that this system cannot form a potential gravitational wave source, and because its binding energy of its envelope is going to be very high. So now we can repeat the same calculations at a lower metallicity, which is where we think that the massive stars that form gravitational wave events have been born. So we again start with two massive stars of 27 and 25 solar masses. But I have lowered the masses a bit because stellar winds are much weaker at lower metallicity, but the rough evolutionary pathway remains the same, where you again start mass transfer on the main sequence. It remains fairly conservative, and the accretor's HR diagram is on the right. And by the end of the donor's helium burning phase, when it's close to core collapse, it has a mass of about 12 solar masses, and the accretor has grown to almost 37 solar masses. Now, if the star manages to successfully explode, it might leave behind something that resembles the secondary in 1908-14 or even a neutron star. And depending on the natal kick that this compact object receives, we can have a variety of separations post-supernova. And if the companion star then fills its Roche lobe, it is again going to be unstable mass transfer because of the asymmetry in this system. And it's again going to form a common envelope. And we can do the same thing about what the fate of this common envelope phase would be by tracking the companion star's radius as a function of time over year in orange, and again equivalently the binding energy of its envelope depending on when it fills its Roche lobe. Again, I can convert this into the equivalent alpha that would be required to eject the envelope, and we can see that alpha in general decreases with time when the star's radius grows and its envelope binding energy decreases. But the most drastic decrease, and when it goes below 1, happens when the star has a radius that's much more than 1,000 solar radii. And this this occurs when the companion star is on the red supergiant branch and it develops a loosely bound convective envelope that's easier to eject. Now, if the interaction happens at that point, what you would do is your common envelope phase would be successful and you would be left behind with the stripped helium core of the star that filled its Roche lobe, which is about 20 solar masses, and you have your companion that could resemble the secondary in 1908-14. And this stripped helium star is likely too massive to explode, and it might just implode and leave behind a 20 solar mass black hole with a 2.6 solar mass compact object. And these two compact objects are going to merge through a gravitational wave driven in spiral and resemble something like the highly asymmetric mass ratio of 1908-14. So to summarize, we showed that we can reconstruct the highly asymmetric X-ray binary that we see in our own galaxy with isolated binary evolution, and that it's likely not going to form a potential gravitational wave source because the binding energy of its envelope when it fills its Roche lobe is likely too high. But we also showed that a similar formation mechanism can work at lower metallicity too. And if the second phase of mass transfer, which is going to form a common envelope, happens when the companion star is a red supergiant with a loosely bound convective envelope, then we can form a successful common envelope phase and leave behind with something that can form a highly asymmetric gravitational wave event. But all of this depends on what is the natal kick that the compact object receives and what are the separations post for supernova. So you're given a standard natal kick distribution. I have shown what the possible sizes of the Roche lobe are post supernova. And we find that for every 100 events that might resemble the highly asymmetric X-ray binaries, we can form one event that has a separation large enough that you might form a highly asymmetric gravitational source out of this. And given that we see two systems that are highly asymmetric in our own galaxy, that corresponds to a local merger rate of about 200, and since 1% of those are going to form events that lead to gravitational wave sources, we can get an estimate of the merger rate for highly asymmetric gravitational wave events. That's about 2 per gigaparsec cube per year, which roughly lies in the ballpark that we get from LIGO, which is about 1 to 23, which is just based on one event, that's 1908-14. So as a summary slide, I'll just leave behind like a speculative slide about other potential analogs that might also form through this similar formation channel and would be interesting to find. Thank you.
Okay, I actually have a question. So when you compared it to the LIGO rate and the population, actually most, like the headline population results omit 1908-14. They don't include it.
Yeah.
And if you include it, it can do funny things to the population. So just clarifying.
Yeah, so this rate is just the single event Poisson noise limited rate of 190814 like events, and it's the only one in its class, so it's just one event, and that's what you get. But yeah, various results like the maximum mass of the neutron star or the presence of a mass gap depend on whether you include or exclude this event.
Even the overall rate can fluctuate.
I see. Okay.
Other questions?
Yeah, so are you assuming you just get a Blau kick, or are you assuming an asymmetric kick for the
No,
neutron
so
star?
you will have a Blau kick just because of the mass loss, but you also need a natal kick to get the binary very wide post supernova. Just a Blau kick will likely not get you wide enough.
Okay.
So you do need natal kicks to, whether it's a 2.6 solar mass compact object or even a neutron star, it would need a strong kick.
Okay, I have another one if no one else has one.
Yeah, go ahead.
So for you, 1700 minus 37 is a really weird object.
Yeah.
Because it seems to be a neutron star, but it doesn't show cyclotron or
Yeah.
pulsations. Do you have any explanation in this scenario for why either of those things might be the case?
So this event has been weird because we still don't know whether the compact object is a neutron star or a black hole. Its earlier mass was estimated to be about 2.6, but now it's slowly gone down to about 2 solar masses, and there have been some claims that they've detected an X-ray pulsation, which might make it a neutron star, but I think the jury is still out on that. But in my scenario, I'm not interested in whether it's a neutron star or a low mass black hole. I'm just interested in something that successfully explodes, and you can form a fallback black hole perhaps out of it, or a neutron star, and that receives a kick.
Okay, no, I was asking more about the X-ray binary, which doesn't show any pulsations and doesn't.
There
show
have been
any-
some claims that it does show pulsations, but it's not, I don't think it's like confirmed that it's a neutron star.
Yeah. Okay.
Cool. I had a question also. Sorry. So you need the low mass compact object to form first
Yeah.
in this scenario. So are there other assumptions that have to be made about the mass transfer beforehand in order to get that to happen, or is that kind of a
Yeah,
natural
so
thing?
in my MESA mod, I have a backup slider for this one sec. Okay, so yeah, so yes, I do need the neutron star or the low mass compact object to form first. And what we find in our MESA models is that mass transfer remains mostly conservative, and that helps you really get down the donor star's mass roughly to a point where it can successfully explode. But there have been population synthesis models where they find that neutron star black hole mergers are roughly always formed when the black hole forms first. And it really depends on, those results really depend on whether mass transfer is conservative or not. What they find is that when it's not conservative, you always form the black hole first. But if it's highly conservative, you can form the neutron star first. And given the tight orbital periods that I work with, mass transfer remains fairly conservative.
Thanks. Oh, sure. We have time for both you and Kareem.
Oh, are your models with rotating stars or not?
Yes, so I'm doing binary models with MESA. I do follow the accretor's rotation. I don't follow the rotation of the donor star.
So with the accretion, so the accretion efficiency is very critical for whether
Yes.
you're going to get
Yes,
mass
yeah.
reversal
Yep.
or not. And in the standard treatment in MESA, the accretor is going to get spun up very
Yes.
quickly with very little mass accretion.
Yes.
And then strong winds are triggered. So
Yes.
do you turn off those strong winds?
So I do use everything. So I do enhance the rotational winds. So when the star's rotation increases, its mass loss increases. But because of the short orbital periods that I'm working with, the system remains tidally locked, and it remains subcritical rotation, and so it can take on more mass. But it really depends on how you're treating tides. I'm using the basic Zahn formalism for tides.
Kareem?
Yeah, so the object you talked about is so close that it probably wouldn't survive. Do we have, or can you say what we know about the wider red supergiant plus neutron star binaries that might be at more favorable separations now? To survive?
So there are some red supergiant donors and X-ray binaries. I think they're called symbiotic X-ray binaries. But we don't have any where the red supergiant is very massive. That's what you would need for a neutron star black hole merger, perhaps. And that is also weird because there is an open problem of like the most massive red supergiants, whether they can actually form or not. So for me, I would need massive red supergiants of at least 30 solar masses or more. And I don't know if these exist or not, and whether they have a detectable rate. That's something you could, they're probably not in the galaxy, otherwise you would have found them. But yeah, it's just some potential analogs that might be needed if you want to form these sort of 1908-14-like events.
Yeah, I don't know, maybe actually Wolf-Rayet star plus neutron star in a wide orbit would be better chance.
Yeah.
I don't think we know of any at that period.
Cool. Okay, so yes, let's thank Neev again.